else. Average and means for quiz 1 and quiz 2. I just read this. So for quiz 1, the mean was 20.5. That means average, right? The median was 22.2. That's the median. 22.2.
Is it score or points?
It was strange. 22.2. What's that?
Is it score or points?
That's out of 30.
It's out of 30.
Okay. That's what I was asking.
That's 22%.
Out of 30. So 22.2.
Points out of 30.
Out of 30, that's right.
That's what I was asking. Got it.
Yes.
Understood.
Right. And for quiz 2, the mean was 18.9. The median was 17.5. So it looks like we actually dropped a little bit. Quiz 2. It's a little surprise because I thought quiz 2 was easy. Maybe it's algebra was harder.
I felt the questions on the back page were like considerably harder than the questions in the homework.
The question on the back page of the
Yeah.
quiz?
Like the third
Is that right?
question.
Is that right?
Yeah.
The last two.
Number 3, question number 3?
Yeah.
Question number 3 was the computer limit.
Yeah.
Oh, I see.
So there were similar, there were
I
somewhat
see.
similar web assigned
Okay.
homework questions, but they were much simpler.
Okay, I see.
There's
So-
the X below.
Okay, I understand. I thought I'd give you a rule that could really simplify it. I told you that when you have a sign of some stuff,
Yeah.
you can erase sign and still get the right answer. So if you use that rule, it's very easy.
See, I tried that and he just marked them completely opposite.
Oh, is that
Apparently I
right?
did the rule wrong.
I mean, if you get it right, if you get it correctly.
But I don't think I used the rule correctly, I guess.
Okay.
You
Maybe
just
we
said,
could go over them and we could
Yeah.
post, like,
I
see
can
an
go over
answer
it.
key.
I can, maybe one of those who got 30 points can volunteer, can let me scan it. You can scan it. Okay, thank you so much. Are you saying you can just do it yourself?
Do you want it?
Either way, I can do it or you can do it. If I do it, I will just scan it and post it and return it tomorrow. Thank you. All right, let's look at those two solutions here. So here, I would suggest that you before do it and write fx equals some function. So you know what, when you say fa, so we know what we're talking about. So let's let fx to be third root of x. Right? That's kind of obvious. Okay? So a equals 1000, x is 1003, is 10. F prime a, I would suggest you don't say dx of that. I know what you mean, but when you write like this, you're talking about the root of a constant, and that would be 0, right? So you don't want to use that. This is not good notation. Instead, what you should do is to, let me just erase this. Say dx of x to the 1/3, and then x equal to 1000. This is the notation that I just mentioned earlier. It's very handy. Okay, and then basically it goes through this 1/3, and yeah, so that is equal to this number, 1000. The negative 2/3, and that is equal to 1/300. This number, do you know how to do this number? You put it on the denominator. 1000 to the third root is 10. 10 squared is 100. So this is the 1/100 times 3. This is just the 1/300. All right. fx equals that? Is that what you meant?
Oh yeah, that's what I was supposed to write.
What you meant is, I mean, both cases, you really meant 1003, right?
Yeah.
Right. 3. So, yeah, 310 plus that number. So, because I already calculated this is 1 over 300, I could just say, I mean, what you write is absolutely correct, but I will just plug in 1 over 300 here. Okay. That times 3. And you erase this as well, so times 3, and that gives you, you don't mean 0.03 times 3, right? You probably meant 1 over 3 or something.
Yeah, sorry.
Anyway, the answer is correct. This is 0.01. But 10 plus, just write 10.01. Yeah. That will be the answer for that. Any questions or comments? Let's move to exercise 2, cosine 61 degrees. Again, I want to begin with explaining what the function is. So let's let fx to be cosine x. Okay. Let's let a be 60, x be 61 degrees. That's okay. 760. That looks okay. Any questions or comments on that? Okay. Let's move to the new section then. That's the case. So we are now moving to chapter 3. So chapter 3 concerns with various applications of derivatives. There's really no new mathematics here, but there will be all kinds of applications, and some of the problems could be quite challenging. Let's begin with the section 3.1, maxima and minima. So if we look at the graph of a typical function, y equals to fx, I think we probably kind of agree what are the kind of maximum and the minimum. So the function starts with a point here and then goes up, down, and up, and down, and up, and so on. So you might want to say this is some kind of maximum, right? That seems to be reasonable because it looks big. And this would be some kind of minimum. All right. Let's label that here. And this is also some kind of maximum. And some kind of minimum here. And some kind of maximum. Now it looks like we got several maximums and several minimums. There got to be some difference. I mean, in a way, this is not really a maximum. I mean, because there's a maximum that is bigger than those. So that's the true maximum. This is kind of a fake maximum. Right? And likewise here, this is not really a minimum because that guy is actually smaller than you. All right, but still, you wanna give them some credit. You know, this is some kind of maximum. So what would you like to call?
Local.
This is what we call a local maximum because it's bigger than any point that is nearby. Okay, so let's call this a local maximum, and this is also a local maximum. On the other hand, this one is bigger than everyone else, so that's called an absolute maximum.
Does global work as well?
You can use the word global. If you're the first, especially if you're the first one who invented the calculus, you write the textbook, use global, everyone will follow you. And you're just born too late. So, I mean, most people use the word absolute maximum. I mean, I understand if you use global. Let's follow the standard notation, absolute. And then some people may probably use global, perhaps. Yeah. Okay, absolute maximum, absolute minimum. Let's make some observations on those. Well, before we do that, we should really give a definition of what are those things. So let's let fx to be defined on some place. Some interval. Let's see, I could be closed, could be open, could go all the way to infinitive, could be some finite. Just any interval. Say that fa is a local maximum. Okay. Or perhaps local minimum if what is true. So what would you like to say? We say this is local maximum if what happens?
The second derivative is negative.
It's very tempting to say that. You really, what's that?
If the line changes from positive to negative, or the slope changes from positive to negative.
I do understand what you're saying, but I do want to say that you don't. What you said are properties. I mean, when you want to say a definition of maximum or minimum, you really just want to focus on the word maximum. Okay. You really want to say something that it's maximum because it's bigger than others or something like that. Okay. So in this definition here, you don't really want to involve with anything like a calculus.
Oh, it's either higher.
Yeah, you want to just go intrinsic, you know.
dimension.
So so what if it's bigger than other values? So let me try it. If fa bigger than fx for all x, is that what you want to say?
In the interval.
For what? For all x? I mean, if you want to say all x, that would not be true, right? Because that x is bigger than fa. So what would you like to say instead? Suggestion?
Whatever interval you're talking about.
Oh, I'm talking about interval from here to here right now. Right? That's my I, from A to B, from this point. So what would you like to say in your definition? I mean, you probably don't want to say for all
You
x.
can write limits.
For all x in I, you don't want to say that, I think, right?
No.
That would not be right. So you want to modify it. How would you modify it?
For all x before the sign change?
For all x what?
Before the sign changes in positive.
Before the sign. So people keep talking about, second derivative is negative, or maybe it goes up and it goes down, derivative is positive and negative. But I want to say that's not even true, okay? I know what's in your mind, but let me give you a strange example. Something goes like zigzag, up and down, up and down, up and down, up and down. You can imagine this keeps on going infinite many of times. Okay, and eventually approaches to the origin and then goes up and down like this. Okay, it could happen. If you have something like this, and what you said now or what you said is true, okay? Right? Do you understand?
I think that
It's
is
not
true.
true.
If all you're looking for is a local max, you take a second derivative and have a negative answer. That tells you that it's a max somewhere. It doesn't tell you it's global. We're looking for a local though. So that is how you find. That
Okay, let
it
me-
guarantees you found a local max when your second derivative is negative.
There are examples that for which second derivative don't even exist. There are such examples.
Fair enough.
And what you, I think one of you said, f is decreasing and then increasing. What I'm saying, this picture shows that it's not always decreasing. It goes like the decrease, increase, decrease, increase, decrease, increase. Right? So it's not quite true that it's always decreasing before that. Okay? What you need to say is it's a local maximum. Local means that it is like a local community for which it is a maximum. So you really want to say for all x which are near A, which are sufficiently close to A. That's what you want to say. Okay. For all x in I that are near A. If you're not satisfied with that, the word near, I mean that seems to be fuzzy. That can be made more rigorous to say for all x in some interval around A. So for all x in near A means all x inside some interval surrounding A. So that is how people define local maximum. Actually, you really should say it could be equal to fx. Because in particular, if x equals a, it becomes equal. You can also define minimum. Same idea. You simply change the sign to change the direction of your inequality. So you simply change this to less than or equal to that is a minimum. So this will be bigger than everyone when x is in this interval from here to here. For this one, you can take the interval to be from here to here. Okay. So there's always some small interval surrounding A for which this is true. We should also define what we mean by FA to be an absolute maximum. Is the absolute maximum, and likewise absolute minimum if what is true.
That is true for
So yes, you want the FA to be bigger than or equal to Fx for what? For all x inside by interval I, right? So that's the definition of local and absolute maximum. So you can ask a question like how you determine this maximum or minimum. You know, determine the local ones, determine the absolute ones, and so on. Let's try to build up some intuitions on that. If you look at a picture, you probably can make some observations. So if you have a local maximum, then what will happen? What must be true? And let's look at the picture here. We look at the absolute maximum. What is true at this point?
Slope equals 0.
the slope equals to 0. Is that right? I mean, the tangent line is horizontal. That seems to be true. And this one is also true. But this one is not quite true because it's the end point. It looks like you have to say, oh, if it's inside the interval, then it's true. So is it always true? Is it true that if you have a maximum or minimum?
No, it's a sharp.
No, if you look at this picture here, then that's not true. What is true at this point?
Doesn't pass.
The derivative does not exist. So you may want to modify to say, not just equal to 0, but sometimes it does not exist. So here f prime equals to 0. Here f prime equals to 0. Here f prime does not exist. And here f prime equals to 0. Here is a maximum, absolute maximum. What happens is that this is the end point. So it seems like those are a few possibilities that we have observed. Yeah.
You said X doesn't have to be a continuous interval, or?
Are you talking about like a 0, 1, and then 8 to 9? Like two different intervals? Is that what
Yeah,
you're
just a
talking about?
non-continuous interval. So you can have the local minimums and maximums on a discontinuous interval.
Yeah, I mean, if you have broken intervals, definitely you can have situation like, something here and then another piece somewhere over there or something. You could have a maximum to be an end point. Yeah. I'm not sure if this is what you're talking about. Maybe not quite. For now, let's focus on the case when the interval is one piece from A to B. Okay. So let's try to make some observation here. We would like to make a statement. Perhaps you can call this a theorem. That is, FA is a local maximum or local minimum or local minimum. Then you would like to say f prime A equals to 0. Okay? And then we quickly observe that this is not quite right because there's a sharp angle kind of pointed there. So then we modify to say, well, either is equals 0 or does not exist, right? Okay, so f prime equals 0 or f prime A does not exist. Okay, so can we make a statement like this?
You're still missing the,
Yeah?
no.
And when it's the endpoint, it does not exist as well?
Yeah, that's assuming A is not an endpoint to make it easier. So before I make this statement, let's let A be inside an interval, not endpoint. Let A be inside an interval I. I.e. A is not endpoint. Okay, then it seems like we have the following statement. And A is the local maximum minimum implies that. Yeah, does that sound good? Seems to be good. This turns out to be true, okay? Well, it would be nice if the converse is also true. Is the converse correct? So, me ask you, is this correct? In other words, if f prime equals 0 and f does not exist, does that mean it's a maximum or minimum?
No.
That's not true. So what's in your mind when you say it's not true? It seems to be true here, right?
A line increasing, going up, leveling out, and going back up.
Okay, okay. So you're saying that the converse is not true. This is not true because of an example like this. Goes up, and then level off, and then go. Like that.
Yep.
Yes. That's right. This is kind of like a fake maximum. I mean, it's like you held some stocks and it's going up, and it's kind of slowing down. You think, wow, this must be maximum. Let's sell it. Right? You sell it, tomorrow it goes up again. That happens a lot. Yeah. You can actually write down the function. What's the specific function that gives you that? It should remind you of a graph of a well-known function. What is that?
X squared.
X to the third power. Y equals x to the third power. And you can really verify that x equals 0 satisfies f times 0 equals 0, but it's not a maximum or minimum. So this is true. Let's remember this. If you have a local maximum, local minimum, then either f1 equals 0 or f1 does not exist. Okay? But the converse is not true. So this is an example where f prime 0 equals 0, but f0 is not a local maximum. It's not local maximum or local minimum. Okay. Let's also establish some general theorem on whether maximum or minimum exist. Okay. So by the way, we're not going to actually prove it, although it's not too hard to prove it. Let me just say a word about why, based on intuition, why this is true. Suppose you have a local maximum or minimum, and derivative, this statement is not true. That means the derivative does exist.